Okay, so let's start today with module 1 itself. So this is going to be the module 1 video 2. So the plan, and I will try to cover the rest of the module 1 today so that we are done with module 1. There are 2-3 things that I wish to cover today. So one is on the neural networks, and there are various forms of neural networks which is also being referred to as deep learning in today's date. So I'm going to talk about it in a little detail. That's one part. The second part that I would like to cover today is around the high level uh, risks. And see, that most of this course is designed around navigating the risks of AI. So we'll talk about all these risks at a later point of time in details, but we are going to touch upon some of these risks and how these risks are, they get into the entire life cycle of all the models and what it can potentially do. So these are the two things that I wish to cover today. So let's start with neural nets or deep learning or things like that. So, uh, the genesis of neural networks is that our brain contains neurons. Okay, and the way human brain processes information is that we consume information from a variety of our senses, whether it is from our eyes or from our ears, visual information, audio information, etc., etc., and the other sensory organs. And all of this information goes to our brain, and there are a set of millions and billions of neurons that process this information, and these neurons, they interrelate, or they make some connections, and all our memory or all of other information that is within our brain is within these neurons. So taking this analogy, and if you would see a lot of algorithms in computer science, whether it is neural nets, which we are going to discuss today, or some other forms of algorithms like genetic algorithm, etc., etc., they are inspired, or they are the inspiration for designing those algorithms comes from the way human beings or human body processes information, or processes a little other kinds of stuff. So let's make a timeline view. So if I would, making a timeline view sometimes helps to understand the progress, and it also gives you a perspective of how things evolved. So I'd say 1943, so which is kind of long back. This is where the concept of neural network was first came into existence. There is a journal called as Bulletin of Mathematical Biology. Okay, so again I'm saying that it's a combination of math and biology. So they started discussing about how the behavior of the neurons inside the brain can be modeled into some form of equations or some form of an information collecting objects, which can be useful in processing. So it was like computer science was also very, very nascent at that time, and artificial intelligence was just on the start. So this is where the neural network first came into existence, and then somewhere in 1949, this is where the propositional logic and those kinds of things were being discussed, and then they started that, okay, let's try to use neural nets for propositional logic. 1958 is the time when the term perceptron came into existence. Okay, so what is a perceptron? Perceptron is similar to how a neurons in the brain, it's a combination of cells, neural cells. So the one piece of entity in a neural network is called a perceptron. So how a perceptron works is, let me try to put it here. So let's suppose this is a perceptron, and it can get information from multiple places or multiple heads. let's suppose it is getting x1, x2, x3 and so on and so on up to xn. And so now this perceptron is going to multiply some weights with all of this information, w2 into x2 dot dot dot, and it is going to put some kind of a function on the top of that, and that's going to be the output. So this is a perceptron. The idea of perceptron first came into existence in 1958. However, what happened by the time we came into say 1969 or 1970s, there was a lot of criticism of neural networks, and there were some researchers which said that all this is not going to take us to the right direction, and they said that a simple function like an XOR function cannot be modeled using neural networks. So they said that this is going to hit a plateau, and neural networks are not something futuristic, and they have a lot of problems. They should not be taken so seriously. At a later point of time, and today, if we have to model XOR operation, we can. But till this point of time, neural networks were single layer neural networks. But as you add more and more layers, not just XOR, even more complicated functions can be modeled. But by the time we were in 1969, most of these neural networks were single layer neural networks, and XOR was something that they were not able to model into a neural network. So now let's come to 1980s. In 1980s, what happened that there is something called as a back propagation. So this algorithm came into existence. So what happens in back propagation is that say neural network is a combination of perceptrons, and these perceptrons are they are into layers. So let's suppose there are some perceptrons in the first layer, there are some perceptrons probably in the second layer, and then there are some perceptrons in the third layer, and so on and so forth, and then there is an output layer which will have singular or multiple perceptrons. Now what happens, and then there is a input that comes to this input layer. Okay, this can be visual input. So when I say visual input, an image, pixels, or a language input, which is word into embeddings and that kind of a numerical input. So all this when there is an input and let's suppose we are working on some kind of a supervised classification algorithm. So you put an image here, and let's suppose the output is only two, it is a cat and a dog. Okay, so now put an image, and then with all these functions for all of these perceptrons, there is some value here and there is some value here. So ideally, if it is a dog, this should be 1 and this should be 0. But while we are training, this might not be 1 and 0. This probably, let's suppose this dog is 0.4 and your cat is 0.6, which is actually wrong, but let's suppose that's how it is done. Now we need to correct this. So we need to tell this system that no, this 0.6, this 0.4 should be 1.0 and this 0.6 should be 0.0. Okay, and as soon as we find that, we find what is the difference between the two, which is something called as a loss function, and then that error has to go back till the input layer and updating the weights of all these neurons that were fired on the way. So this is something that is called as a back propagation. This algorithm came into existence in 1980s, and this is where a lot of more and more complex models could have come into existence. Now or maybe I'll pick that up later, but by 1990s, the pace of research on neural network was slowed down. Why it slowed down? Because neural networks were very compute hungry, so it needed a lot of fancy hardware, or it needed a lot of big machines, which only very few companies in the world could afford back then. Even now there are only very few companies that can afford to have these kinds of big machines. But the pace came down, and the data was also not that sufficient, and it came into some kind of a standstill. Okay, so let me now get more deeper. Let's keep this on. So I'll say, okay, so let me take this from here. So 1989. So there are various forms of neural networks. So what I was showing you here on the top is feed forward, very basic and primitive neural network. However, there are various forms of neural network, and you don't have to get into very details of the math and all the equations that go through for most of these neural networks. You need to have a basic overview. So I'll try to keep it simplified as much as possible. So in 1989, there is something called as a recurrent neural network that came into existence. What happens in recurrent neural network is that the neurons or the perceptrons, they take a timeline view. Okay, so when I say a timeline view, anything that is a sequence of information across time, that needs to be modeled. So it can be audio, it can be video, or it can even be text. So there is something as time t, there is something as time t plus 1. So the input to time t plus 1 is coming from time t. So this is called as a recurrent neural network because it reoccurs. So that's how the term came into existence. So this came into existence in 1989, and sometimes in middle of 1990s, or I think it was 1997, there is something called as LSTM that came into picture. Now LSTM stands for long short-term memory. So what happens in RNN is that let's suppose there are a set of these states, and this is from this you come here, from this you come here, from this you come here, and from this you come here. Okay, now the input for this is only going to come from here. But what happens in some kind of say text problems, if I say that the cat jumped over the fence and broke its leg. Okay, so when I'm saying that it broke its legs, it means that I'm referring to cat. Okay, and it's not referring to say broke. So there needs to be some kind of long-term and a short-term memory that helps us to put this kind of relationship into practice. So let's suppose this is the place of time where we are, and this is leg, and somewhere back here is cat. So there needs to be some kind of link between cat and leg rather than just broken leg. So this is a problem that was being faced by RNNs, and LSTMs came into picture in say 1997, which helped with putting this long-term and short-term memory in place. So that was 1997, I suppose. In 1998, CNNs came into existence. Okay, what happens in CNNs is, and let me try to delete this so that we can talk about other forms of neural networks. So what happens in CNN is, and this is more for text or sequence to sequence kind of information. CNN is more for visual information. So in case of CNN, what happens is, let's suppose there is a picture. Okay, there is a picture of a man, and in a picture there is the information is generally contained in a immediate neighborhood. So when I say immediate neighborhood, the features or the information that you are processing, the neighboring information can have a very good impact on the processing of whatever you are doing, whether it's a classification or anything else. So in a CNN kind of a network, there is a concept called as convolutional filter. So, and this is all there in the notes of GARP as well, that you need to understand some of these terms. So let's suppose there is a 2 by 2 matrix, and because we are talking about images, and it has information about the pixel values. Let's suppose we are keeping that to say grayscale 0 to 256 or so, and there is some information here. Let's suppose it is 10, it is 15, it is 20, it is 6, and let's suppose this is 10. Okay, so now the convolutional filter, which is going to be a n cross n filter or k by k filter, it's generally a small filter. Let's suppose this is a 2 by 2 filter in this case, and we make it like 1 0 0 and 1. How do we get these values? That is not important right now, but we take this filter over this image, more like a sliding window, and we take this from left to right, and whenever it slides over these 4 pixels, the numbers are multiplied. So 10 multiplies 10 into 1 plus 15 into 0 plus 6 into 0 plus say 10 into 1. So whatever output we'll get, so this is anyway 0, this is anyway 0, so 10 and 10 makes 20. So in your next layer, instead of putting these 4 boxes, you are going to put a number 20. So what this does is it reduces the dimensionality to some extent, not huge, because if it is a 2 by 2, it will only reduce this 1 by horizontally and 1 vertically. But if it's a larger filter, it can reduce, say, so let's suppose this is k by k, it will reduce this by k minus 1. So convolutional filter is going to give you the neighborhood aspect of the pixels, and it is going to so that's how convolutional network works. And then there is another layer which is called as pooling layer. So in the pooling layer, what happens that the purpose of pooling layer is to reduce the dimensionality of information. So if it's a pooling is let's suppose we want to pool in a 2 by 2 kind of a matrix, then we take the 2 values and we try to take their average or any other statistical method, and we'll replace these values by that average. Okay, so convolutional neural network net at the end of the day is for processing images or any visual form of information, and it's a mix of convolutional layers and pooling layers. And once so these CNNs came into picture, there were a lot of people who pre-compiled a lot of such information and created some networks which could identify say 0 to 9 numbers or some kind of an OCR kind of visual processing of information. So there is something called as LeNet, which came into existence around the same time, and it was one of the best models or the most accurate models to find out say to identify numerical numbers written as images. And at a later point of time, maybe a decade after this, there was something called as AlexNet, which was nothing but a larger version of LeNet, maybe 100 times more, and this was like a near perfect OCR for numerical digits. So all of this came into existence. So that's the CNN side of stuff. The next big thing is say around 2014, and I'll see if there is something that came in between, but I think 2014 there is something called as GANs. They came into existence. So GAN is a generative adversarial network. So it has two parts. One is a generator and one is a discriminator. And they are adversarial in nature. So it's like they work against each other to iteratively to a state where the balance and discriminator is not able to identify what is right and what is wrong. So let me give you an example. For example, a generator is trying to create some images of, say, let's suppose fake currency, and the discriminator is some kind of a police or some kind of a check which is going to, some kind of a supervised learning, you can say, which tells whether the currency is fake or the currency is real. So it is going to say, okay, this is so initially in the first few iterations the fake currency is going to be very, very bad, and the discriminator is going to say that, okay, oh, this is not the right currency. But over a period of time the generator becomes so smart that it creates some kind of output that the discriminator is not able to tell whether it is real or fake, and that's the time when we stop these iterations and the generator becomes a very good image generating thing. So where is this used? For example, let's suppose in today's world, when most of your deep learning networks need a lot of images or need a lot of data, and tomorrow if you want to build your own OCR kind of a framework or OCR for a language, and you don't have enough data, so you can have a generator for each alphabet, and it can give you a noised image of all these alphabets in various fonts, various orientations, etc., etc. So this is where this GANs are used. So it came into existence in 2014, and then there were I think a lot of diffusion models that also came into existence around 2014-2015 only, which also are visual information, the diffusion models. And then around 2017, not around, but in 2017, there was a very, very breakthrough framework in deep learning kind of networks, which is something called as a transformer. So what happens in case of a transformer is that there is a encoder which encodes the input into some kind of an intermediary, okay, and then there is a decoder that uses this intermediary and decodes this into output. And there's a lot of stuff that happens in between, but for today we are not going to get into the details. We'll get into these details when we study or when we go through chapter 2 on encoders and decoders and transformers, etc., etc. So this is the same framework which runs your ChatGPT, which runs your most advanced say text-to-text models, language translations, etc., etc. What happens, there are various kinds of transformers. There can be transformers with only encoders, and these can be your models like your BERT models. So BERT models, or any form of text embeddings, contextual text embeddings that are there in the open market. Okay, so those are encoder models. There can be some models which are only decoder only models, and these are your models like your GPT, various forms of GPTs or any LLM. So they are decoder only models. And then there can be models which use both decoder and encoder. These are models like say T5 by Google, which translates say one language to another language. So all kinds of machine translation and those kinds of models. So so that's the brief history of deep learning, and this is something that you should be aware of. Deep learning, neural networks, whatever you want to call this. Okay, so let's move into next topic. We'll get into some form of more details about this in module 2, but I have given you a brief overview, because when I'm going to talk about the risks and other parts associated with deep learning, you should know briefly today about the nuances or how complex these models can get, etc., etc. Okay, so when when we started doing this kinds of modeling or some kind of predictive analytics, statistics was all we had. Okay, and or you can also call it some kind of econometrics. Okay, so that's how the modeling and all of this information started. Then this moved to machine learning, and when I say machine learning, it can be supervised, unsupervised, semi-supervised, reinforcement learning, etc. And then it moved to AI. So a lot of literature uses some of these models interchangeably, especially the ML and AI. But when it comes to most of the references that GARP will make, when they talk about ML, this is traditional machine learning, and when they talk about AI, this is the new forms of all what we were discussing, the machine learning and deep learning forms of predictive analytics. So that they refer to as AI, and these models, when we're talking about statistics, your input features or in in the range of say 20. When we got into machine learning, we got into say 50, 60, but still 100 features, or the size of the model was also not very large. But as we navigate into AI, and things have become very complex. The models have become very large. Now as of today, they don't disclose the size of the model, but when people do some kind of a reverse engineering, and the latest GPT models is more than 1 trillion tokens. Okay, so 1 trillion parameters. So these models are gigantic. These models are impossible to train on commodity hardware. These models are almost impossible to host on a commodity hardware. You need to host them on cloud, you need to host them on very large servers, and it is also very difficult to understand these models, how decisions are making. So we start with the problem of inscrutability. So what does inscrutability mean is that the problems with some of these AI models is that these models are not explainable, and that these models are not interpretable. Now these two terms also may sound similar, but the difference with these two terms is that when it comes to explainability of the model, it refers to the explainability after the decision has been made. Okay, so let's suppose there is a person, and let's suppose I go and apply for a loan from the bank, and the bank denies me the loan. Then there needs to be somebody who should tell me, who should explain to me why my loan was denied. Maybe I didn't have a great credit score, maybe I my financial health is not that great, or I don't have a big history of being into the financial systems, etc. So somebody needs to explain to me the reasoning. Okay, reasoning for the final decision. So that's the explainability part. Interpretability is more to do so with the design of the system in itself. Okay, so even before the decision is made, we need to have some kind of an interpretation that the model that we have created, this takes some kind of say demographic data, some kind of financial data, some kind of say data from social sites or social networks, and it tries to say most of your decision making is coming say 60% from financial data, maybe 10% from let's suppose somebody is doing a lot of into adventure, and gets into some dangerous forms of hobbies, whether it is skydiving or those kinds of things, then if that person seeks to buy an insurance, the premium for that insurance needs to be more versus somebody who spends their weekends going to library and read books. So that kind of information can come from social networks, and demographic data can also be important. So let's suppose this is 30%. So this is how your features are kind of weighted, and so that's more to do so with the interpretability of the system. So the problem with all these gigantic AI system is that they are neither explainable not interpretable. So if there is a decision that is wrongly made, it is and even if we understand that the decision is wrongly made, there is probably no chance of fixing that, because most of your models have become almost impossible to do a point fix. They can be retrained, and they can be retrained from scratch, etc., etc., but there is no possibility of a point fix. So both these models are inscrutable, which means that they are not explainable, they are not interpretable. Now there is also a small topic of PCA. I don't know why GARP has put PCA here in module 1 when they are talking about risk. This is more suited when we talk about say unsupervised learning at a later point of time, but just to make sure that I am touching all the topics in the same sequence as they appear in the study material, I'll just briefly talk about PCA, and we'll get into more details later. But PCA, which is principal component analysis, this stands for the dimensionality reduction. Okay, and it is more of a statistical means to reduce the dimensionality for any form of numbers that you give. So let's suppose if we have let's suppose 100 features, and our models, most of the PCA was used when we were in the era of machine learning or econometrics. So if my model is not capable of handling 100 features, or if I'm doing some kind of a feature engineering and find that some of these features were highly correlated with each other and I want to reduce the dimensions, that's where PCA comes into existence. GARP says that it is unsupervised learning, but then if you read more literature, you can also read that PCA is more of a statistical means to reduce the dimensionality rather than an unsupervised machine learning way to reduce dimensionality. But at the end of the day, PCA helps to reduce the dimensionality, whether it is in the form of an input or even let's suppose we use some kind of a complex AI model, and as an output, let's suppose we are using an encoder only output, and we are getting some kind of text embeddings, and text embeddings are generally vector, which is say 1 by 300, 1 by or larger than this. So if I'm having text embeddings for words, and I want to represent it into a two-dimensional space, that's also where my PCA will help, and I'll put everything in 2 words. So if I have tea here and coffee here, and let's suppose I have say beer here, so these will be more close to each other rather than this. So this is also where if you want to visualize some information in a reduced dimension, because when you go to senior stakeholders and if you tell them that this is say a very large space, and in that kind of an hyperspace there is similarity between these two and not between these two, people will not be able to visualize this information, and that's where PCA will help. So this is going to be PCA component 1, and this is going to be PCA component 2. So a lot of large dimensionality can come into a smaller space and it can be visualized properly. So that's about PCA. I don't want to get into more details right now, because it will break the flow of what we have discussed till now about deep learning and the nuances of deep learning. Okay, so coming to risks again. So let's go back to risks of deep learning. Let's start with something called as we have already spoken about the risk of inscrutability. So when I say risk of inscrutability, this is, models are not explainable, models are not interpretable, and you cannot do a point fix. There I can give you one or two examples where this created this particular problem helped or did not help companies to scrap some of their projects. So Amazon was building one system where they were trying to look at the CVs and do some kind of a screening, where they were saying that, okay, who should be called for an interview and who should not be called for an interview. And over a period of time, they realized while they were training this algorithm that this algorithm has a bias, gender bias, and it favors males. Okay, why it favors males? Probably because the data that it was trained on had more males than females. And even though they realized that there is a problem with the model and it is not in the favor of a particular gender, they were not able to fix this because the data itself was bad. Even if they removed the gender from their CVs, the rest of the data in the CV, there is most of us would have seen that men and women may have their own expression, the way they write, the way they their hobbies, or if somebody is saying that my hobby is more say adventure, or I like sailing, or I like those kinds of things. So the patterns in your wordings, or the way you would describe yourself, the neural networks have become so smart that it is going to indirectly derive that this is from a male and this is from a female. So they were not able to fix this problem and they had to scrap this. A similar example is which happened a couple of years back, and Apple and Goldman Sachs, they were trying to give a credit card. They were trying to offer a credit card to their customers, and again the same problem. The credit limit, or the decision to give the credit limit, was biased. Okay, and it also gave more credit limit to males rather than females, even if they had the same kind of financial history and same kind of financial appetite. Why? Again, because the data that was fed into the system had more males than females, and historically males had been given more debt and more loans and higher credit limits. So this got into some kind of legal troubles for them, and eventually the card was withdrawn. But net at the end of the day, there is a risk of inscrutability, and because of which a lot of projects have gone down the drain. The other problem is with respect to privacy. Since these models are very data hungry, they try to extract the information about the users from wherever they can. So it can be social media. So let's suppose they go to Facebook and they find out your likes, what kind of posts you like, what kinds of posts you dislike. So all of that can give a fair indication about your, say, political views, your sexual orientation, your religious orientation, your ethnicity, and everything else. So and which is a very private data. You are not putting this so directly on the Facebook, but because the algorithms have become smarter, they will come to know about this. So that's the problem. That's a privacy problem. These algorithms will come to know what is it that you may want, and because they become so smart, they can also manipulate you, so if they know that you like a particular party or you like a particular political ideology, they can manipulate you by sending you some posts or some kind of information which will make you even more headstrong that okay, yes, my thinking is right. So that's on the privacy side of things. Then another risk is risk of over reliance. So what happens once you know that there is an automated way of doing things, your own expertise to make decision making gets reduced, and you may get into some kind of a self doubt whether what if you are going against the machine. And this has it has been there traditionally from a long time. You need to be extremely smart to follow your gut rather than following what is coming from the machines. It can be like your if there is somebody, if a pilot is in a cockpit and the autopilot is telling him or telling her that he needs to, there is a problem with the fuel and he needs to go back, but if he is smart enough to understand that the weight of the aircraft has not decreased, etc., or some other kind of an causality, he needs to be very smart and to say that no, what I'm thinking and what I'm doing is right rather than what the machine is telling me. Similarly, in a bank, if there is somebody, or if the model is telling somebody that we should deny a loan to somebody because that person has a very short history of stay in a particular country. But if that person is say, let's suppose somebody went to US and he's taken admission in MIT or Stanford for doing a PhD, and he has a good bank balance maybe back in his native country or in the home country, and he is quite a sensible person, then it might not be a good idea to deny a loan to that person. So there is a problem of over reliance. Another example is that this Google self-driven car, this self-driven car that we are talking about, and it killed a pedestrian. Why? Even in spite of the fact that there was a driver sitting inside the car for emergency, because the car was doing so well and it had not taken a wrong decision in months and months, the person was not able to slam the brakes at the right time because of over reliance. So and then in the modern world, in this chat GPT, if it gives you some information, if that information might be 90% of the times correct, but in the remaining 10% of the time, since we become so over reliant on that information, we don't double check it, and this is quite a common term, that all these terms hallucinate. Okay. And mathematically it is proven that however good we get with these transformers or decoder only transformers, since the data is sometimes is right, sometimes is wrong, there is a lot of misinformation across the world, the models will always hallucinate. So mathematically it is impossible to build a model that will never hallucinate. So factual correction might sometimes be correct, most of the times be correct, but sometimes it might be wrong. So our over reliance with ChatGPT can also create it's a risk which we need to be aware of. Then there is let's call this as individual risk. Now what happens in case of an individual risk? All this over reliance, etc., is an individual risk as well, but once the decision that is being done impacts the day-to-day life of an individual, it becomes an individual risk. It can be again the loan, or it can be any other decision that the machine is taking which can impact an individual person. Okay. Second is the risk to organizational risk. Now, in case of an organizational risk, we spoke about Amazon, we spoke about Apple, we spoke about Goldman Sachs. There is a risk of reputation. Okay, so if they come up with something which is not regulatory correct, and if they are fined, then it can harm their reputation. So, and then there is false confidence. Okay, so there is a risk of false confidence. So sometimes what happens that in your MVP or a POC stage, the algorithms do very well, and and it may still do well, but there can be very rare scenarios where these algorithms will get into some major troubles. So the organizations get into some kind of a false confidence that yes, we can remove the human from the loop and everything can be done by the algorithm, and it can reduce your time of processing, and it can make my operations more optimized, etc. And they get into this kind of a false confidence, which can get them into legal or reputational troubles in the end. So that's on the organizational risk. Then there are risks with respect to, say, society at large. So these are societal risks, and of course the first risk is the risk of loss of jobs, or unemployment. So what is going to happen is some of these jobs which are more say paperwork driven, or if there is a standard operating process that needs to be followed, those are the kinds of jobs that can be automated. So there is a problem with it. There is a social problem of how do we redeploy those people, especially the ones that do not have the digital skills. So your difference of disparity between people with the digital skills and people without digital skills is going to be huge. So that's going to create some kind of a social unrest as well. There is also a societal risk at large. It is going to favor countries which are either technically more sound, or they have a larger population. Okay, because most of these models will need a lot of data. So if there is a country which has more population, it can engage its population to get all these things or all these models. Generally it is found that a larger model gives you a better result rather than the smaller model. So people with larger scale or larger population, and countries which have technology, especially the digital technology or the AI technology, are going to become very powerful. If we see today, most of your cloud and AI is coming from either Microsoft, or is coming from Google or Amazon, or IBM. Primarily these are the companies that are holding most of, or maybe Meta and etc. So most of these countries all come from US. There is hardly anything that is outside of US. There can be few companies that can be from, say, UK or somewhere in Europe, but think about countries which are, say, somewhere in say Africa, a country like Somalia, which will have a small population and not that great in tech. The difference between haves and have-nots is going to become more and more evident. And probably the last risk is which might not be so much of a risk, but let's talk about it. It's called the existential risk. This is something that the existence of humanity itself can get into a risk. Maybe not immediate, but as AGI becomes more and more powerful, and as these machines start getting into more agentic and independent decision making, and they can communicate within each other, the humanity itself can get into risk. So that is that's all what I have for today, and this brings us to the end of module 1. Now we'll start with module 2. The module 2 is going to be bigger, like we are going to be more videos. The module 2 is going to be based out of, say, I'll break that down into 10 videos. Each video is going to get into one topic: supervised, unsupervised, semi-supervised, reinforcement learning, and then get into how do we quantitatively evaluate the goodness of algorithms, what kind of KPIs, what kind of statistically, how do we validate whether our output is good or bad, and then get into more NLP, generative AI. So again, there are going to be 10 videos for module 2, and then we'll get into module 3, 4 and 5. So thank you very much.